always seems impossible, an intro to him. But I was actually looking for his, right? So everyone knows what a binary search tree is, right? What is the significant property of a binary search tree, by the way? Fundamental property. Can someone put it in the chat? What is the fundamental property of a binary search tree? Anyone wants to put that in the chat? What is the fundamental property of a binary search tree? The moment I say binary search tree, what should come to your mind? Nobody, Searching for Katrina Kaif on Google. I think she was the most searched celebrity, I think, last year, right? Or maybe Deepika Padukone now. Talking of movie stars, you should all go watch Jolly LLB. Hilarious movie. Very nice movie. Well done by Akshay Kumar. Probably that is more interesting than a data structures class, Okay. So nothing comes to mind when you talk about binary search tree. If nothing comes to your mind, then nothing will come to your mind when we talk about optimal BST also. There you go. Whoever put that, let's see who put that. Coordinator, see? ASN Garu put something there. Sri Prakash, there you go, perfect. It's all about, see, you can read the chat, right? It's put for everyone. The left subtree of a node has a key less than or equal to its parent's node key. All the left side have keys which are less than the root, and all the keys which are to the right of the root are greater than the root, right? So there's certain, what you call it as certain order in which these are done. Okay. Surprisingly, my WebEx crashed after a very long time. I don't know if you see my screen or not, but it crashed. So if at all I get disconnected, I'll log back into WebEx. Okay, bear with me. Is my WebEx still there? Can you guys still see it? No. Okay. My audio might still be there. Let me get into the WebEx part. What I said was take the, I kind of gave you a quick introduction to what an optimal binary search tree is, right? Right, I gave somewhere in one of the slides before, and I said when we talk about optimal binary search trees, we talk about the keys which go into the tree and the frequency with which they occur. Okay. So, and then I defined how you compute the cost. Correct? So where is that? Let me check where you compute the cost. Give me a second. Okay, so we said we do a, I had it right here, right? This is how we define the cost, right? The level of the node multiplied by its frequency. Okay, and we said the keys occur in a certain frequency, and we gave an example of online dictionary or any of the word thing, right? That you are doing, that you do on the internet. Like for example, when you are now, if you go Google search, when you're typing your sentence, Google automatically fills up the possible words. Same thing on your cell phone when you're doing texting, right? It gives you the list of possible words. So it is actually using the optimal binary search tree principle to help you type your text fast by giving out what are the possible words. So you just select that word and then you don't need to type all the characters. So that means we have certain keys. Keys are your characters in the case of text messaging. Could be any other keys. And then you have frequency of occurrence. And when you arrange them, right, I gave you this example. See, when you have 10 and 12 as the keys, and 10 can occur 34 times, and then 12 can occur 50 times. Between the two numbers, 10 and 12, there are only two ways of arranging them, right? 10 can be the root, applying the binary search tree principle. 12 is greater than 10, so it goes to the right side of 10. The other option is 12 can be the root, and since 10 is less than 12, it goes to the left side. So in the case of diagram 1, the cost is what we define how we are doing the cost. So it's a formula. Take the level and multiply by the frequency. So if you see 10 is at level 1. We're not talking at 0 here, right? So level 1 times the frequency, which is 10 comes for 34 times. And 12 is at level 2. 2 times frequency is 2 times 50. So total is 134. The other way around, you get 118. So obviously arranging as diagram 2 would be cheaper, right? You want the cost to be low when you're traversing all the nodes. Please share the screen. Wow. I'm sharing the screen. Thank you for pointing it out. So this is what we said, right? This is how we define the cost. And I gave you this example. Okay. Do you want me to repeat the explanation or you get it? Okay. So these are the two ways of arranging the tree of the keys 10 and 12. 10 occurs. I mean, it's a known frequency now. You can ask me a question, how do we know that it occurs 34 times and how do you know 12 occurs 50 times? It's data analytics, right? So we know the most used words, okay? So over a period of time, the AI system learns and it knows how the frequency of occurrence of these different characters, numbers, whatever the case may be. Okay. So if you see 10 and 12, you see the cost of tree 1 is 34 times 1 plus 50 times 2, which is 134. The cost of tree 2 is 50 times 1 plus 34 times 2, which is 118. Our goal is to always minimize the tree cost when you're traversing the nodes, right? So you want to take the diagram 2 approach. Okay? That was a brief introduction that I gave you to optimal binary search tree. So in these two, second one is the optimum because it gives you the lower cost. That's how you define an optimal binary search tree. Okay. Just a small example. Then I gave you three keys now. Instead of 2, I just made it 3. Kite, you can see the screen now, right? I'm sharing my screen. Okay. Now with these 3, and then I gave you the frequency of occurrences, right? So I asked you to draw at least 3 binary search trees and calculate the cost. Okay. So let's play a game here. Come up with the 3 BSTs. 20 root. Okay, there you go. Sri Prakash, good. So Sri Prakash said 20 root, 10 left, 12 right of 10. Okay, 142. 20 is the root. Okay. Okay, what about other options? This is the only way to arrange the tree. I didn't ask for minimum cost. I simply said, what is the cost? Okay, so hopefully you would have done that. See, from here, I don't know whether you have done it or not. It seems to me the deadening silence tells me that you probably thought you can go off and then goof off or enjoy a nice lunch or a movie. Now you're doing it, but I'm glad you're doing it. See, Prakash, that's good. 12 root, 10 left. See, it's so easy, right? It's an easy problem to do. Okay. Now I made you do 3. Why did I make you do 3? As you can see from see, Prakash, yeah, put it to everyone. Correct. Yeah, put it to everyone. Don't put anything to private. These things everyone can learn from it, right? Okay. See, depending on how you organize the tree, as Sri Prakash is putting there, the costs vary. Okay, that is what we wanted to illustrate. Okay, okay, good. Now let's see, where am I now? I wanted to go briefly, then you get to do some real hands-on today most of the time while I'm taking a nap. I'm just kidding. I don't take nap like that. You probably got a heart attack. Oh my God. Professor is taking a nap in the classroom. Even though that's not uncommon, by the way. I have seen professors like that who actually put students to sleep the other way around. Okay, so again, why do we need this concept? Because it's used all over the world, all over the place in many applications. And the standard textbook example is dictionary. Okay, some words occur more frequently than others. Okay, so if you know the frequency of the individual keys beforehand, then we might attempt to create a optimal binary search tree. Okay, now notice one thing here. Typically, it works great when it's a static tree, meaning you don't do many insertions. Okay, you organize the tree already based on the frequencies and things like that, so you don't have to touch it. Okay, so formally speaking, you are given a sorted array of keys, 0 to n minus 1, or is it depending on which literature you read and which PowerPoints you review, they call it from I to J. Okay, you have a bunch of keys, and then you have a frequency. That means they give another array, either another array, or I can create both of them in a table too, right? Two-dimensional table. So you have the frequencies, which also go from 0 to n minus 1. Each of those things correspond to the key. Okay, frequency I corresponds to frequency of key I. So you want to construct them in such a way such that the total cost of all the searches is as small as possible. The goal is small. Just like how Sri Prakash put it here. They put three varieties there, and then 168 is the minimum cost that they were able to arrive at. Okay. So here is another way of nice slide. I like this slide. Some professor made it. Tampere University of Technology, as you can see. Right? So another way of looking at of n different keys. We want to build a BST of these keys. Now for each key KI, notice one thing, a slight formality compared to the previous slide. We have a probability PI that the search will be for KI. So instead of giving you hardcore numbers like 34, 50, 17 and all that, we formalize it, right? So we give a probability, okay? That somebody is going to search for that particular key, okay? Now when you're searching for something, You may not even find values in the tree, right? So what typically we do, I mean, I don't get into that detail. I don't think I show you any slides related to that bullet 4. The way you do that is when you build the tree, for all the other values which are not in K, you use some dummy keys to say that you have reached the end of the road and you didn't find the key. Okay? So if you look at the notation that the author is using here, D0 represents all values less than K1. Dn represents all values greater than Kn. It's some formal notation. Okay? But we got the essence, right? The essence is to minimize the cost. Kite woman, please mute yourself. I keep muting them and they keep unmuting them. Okay, here is a challenge for kite woman. Either you mute yourself or sing as Raga or Annamacharaki. I'll mute them and they have to stop sharing. The question I asked was, what is the observation that you can make by looking at that fifth BST? Somehow we came up with that. What could be that algorithm? What is it that it is giving me some idea, some hint about how to approach this problem? That is the question that I asked. Mute yourself, please put the answer in the chat. Okay, so anyone can guess what could be the algorithm? What is the shape of that algorithm? You already have the answer there. 20, 10, 12 is the right answer there. Okay, and then you know the frequency, the input key and the frequencies. So how do you map those two? What comes to your mind when you look at those two things? Other than they are beautiful numbers, nothing? Absolutely nothing. No, you're all too smart guys. I have great faith in my alma mater, JNTU, you know. You're all bright students. Some of you should be able to answer that. Make some guesses. It's okay to, remember, you can make all kinds of guesses. No guess is stupid. It's all in the spirit of learning. Do I place the lowest frequency item at the root? Yes or no? Do I place the lowest frequency item at the root? So somebody answer whether it is yes or no. I'm assuming you are able to hear me, right? Okay, let me pick on the wonderful girl in Kite W, since I see the video. The one in blue, is it peacock blue or what, some blue color? Or I don't know whether they call it blue. The girl is looking the other side, not into the camera. She's now trying to hide. So you answer, yes or no. You're staring down. Don't stare down. Tell your coordinator there, type yes or no. Do I place the lowest? Okay, that is too, yeah, Sri Prakash, don't get into too esoteric stuff like that. Keep it simple. The question is, do I place the lowest item, lowest frequency item at the root? The answer is yes or no. We didn't talk about heaps and all that, right? So no point talking about max heaps and all that yet. Okay. So do I place 10 at the root? So we have 10, 12, and 20. Do I place 10 at the root to get an optimal BST? Yes or no for that? This should not take more than 5 seconds to answer, right? You're looking at 5 pictures there. The very first picture, you see 10 at the root. No, yeah. So why should it take that much time to answer? Right? 10 seconds is one of you should answer. Good. It's no. Okay. Do you think it's very likely you should place the highest frequency item at the root? Yes or no? See, Prakash, you don't answer. Let someone else answer. Do you place the highest frequency item at the root? I want somebody from Kite W to answer. Or the faculty coordinator there, make sure they answer. I'm asking Kite W, that is the Kite woman, to answer. Okay. Yeah, Sri Prakash, I know you know it. You're excluded from this question. Yeah. Do you place the highest frequency item at the root is the question. Yes or no? Okay, let me move to Kite Guest. I don't think that is Kite Woman, right? Kite Guest, I don't know if the same class or not. Do you place the highest frequency item at the root? Yes or no? Okay, I'll go back to yes. You got it. Okay, that's good. So we said we will not place the lowest frequency item at the root, but instead we'll place the highest frequency item at the root. Okay? All other colleges, people who were shy, Kite W and all, you got the answer, right? Very likely, right? Looking at the picture, I'm just making some observations out of the pictures there, right? You have 5 trees. Now, what is the rationale for placing the highest frequency item at the root? What is the rationale? What is the justification for that? Can somebody answer that? Why do you think that is the case? Why do you think that highest frequency item should be at the root? Thank you, DMS. Yeah, the answer is yes, correct. But why do you think that is yes? What is the rationale for placing the highest frequency item at the root? Sri Prakash, you are also welcome to answer that. It's common sense, right? When we want to start looking for an item in a tree, where do we begin? We begin at the root, right? We don't begin at the leaves. So the most used item should be at the top, right? In this case, root, right? So that way we are done with our searching, correct? If I put the least frequently used item on the top, that means I have to go another level down, right? Now, if the tree is organized properly, then it could be log of, you get the depth of the tree, log of n. But if the tree is skewed like completely right side, like as you see in in picture 1 here, or completely left side, there's a potential the algorithm would execute order of n, not instead of log of n2, right? So that is the common sense approach, okay? Now, I'm not saying you just use one simple criteria to build the tree, okay? But I'm saying these are the type of observations that you make. In real life also, guys, when we do the algorithms and all that, when we do a lot of this databases stuff, where we group data together and all that, these are the type of observations that we make. It is not just theory, right? Theory is good. Theory comes in handy. I'm not saying theory doesn't come in handy. There's a lot of practical insight that we gain observing these things, right? When you take the database class also, you will actually learn some of these things. We get into things called normalization of data. We get into first normal form, second normal form, third normal form, Boyce Codd normal form, and so on. Normalization is theory, okay? Great theory. But the practical reality is the way we design the database tables is not based on just theory. It is also based on the fact what type of queries we make to the database, okay? Because when you have a database, as a user interface, there will be a lot of queries, right? People will be running queries. So depending on the type of queries, we will design our database accordingly. Because if my query dictates that certain, let's say I'm getting, guys, you really have to mute yourself. Okay, 1 second. I want to stop sharing for a second with the items at the bottom, correct? Single time I have to bring data from two different tables. I have to do a join statement, meaning I have to join those two tables. Join is like matrix multiplication. It's a Cartesian product, basically. I cannot say matrix multiplication, close enough. It's a Cartesian product. Okay, Cartesian product, if I have 1,000 rows by a table and another 1,000 rows table, a Cartesian product of 1,000 by 1,000 is 1,000,000. Okay, I have to do 1,000,000 computations because the data is in two different, and followed by a selection of the rows, followed by a projection. That is how the database works. So when I know that I am going to get the data from two different tables, I'll say to heck with the two different tables. But then the practicality says, you know what, I'm going to combine those two tables into one. So that way, when I'm looking for that particular data, it is in one table. I do not have to do 1,000 times by 1,000 times table multiplication. Saves time. Okay. So there are some common sense type of thing that we do, and so that those are the type of observations we make first before we get into the complete algorithm development. Okay. Okay. So this one we don't have to understand it right now because I want you to understand the code level, right? But what happens is we calculate the cost, okay, of ij. Ij are the elements, right? I to j, remember? Element I to element j, and with the frequencies I to j correspondingly, right? How do we compute the cost? We have first element frequency of k. So that is the root, okay? It's always at the root, right? The root is level 1. So 1 times frequency of k. Now the first element corresponds to the root, okay? Plus minimum of rest of it, right? You already did k. So you take IR minus 1, then from IR plus 1 to j. It's mathematical thing. You can easily figure that out. I gave you the explanation there. And then you add the sum of the frequencies. That's what we have done, right, in that simple example. Okay. Now you can convince yourself that that formula works, okay, as a homework. But for now, we'll move on because I want you to practice your code, right? Okay. Now, so we have about 45 minutes. I thought we would have more time than that. Actually, we only have 40 minutes. I thought we'll have almost an hour. I didn't realize that that simple stuff in the beginning takes more than half hour. What I'm giving you here is a piece of code. Okay. So there is an optimal. We are building an optimal search tree. Okay. And this is the code. Part of the code is on this page. Okay, the good comments and all that there, right? Okay, and then the next slide shows you the driver program. You know, whenever you write C programs, you write your main, right? Main is where you have a driver program. So what do you have in the driver program? You have the keys 10, 12, 20, 34, 850. Same thing that we took there earlier, right? Okay. So what we want to print is the cost of optimal BST. Just like how Sri Prakash put that cost 142 by putting 20, 12, and 10, right? So you already know what the answer is. Okay. What I want you to do in groups of 2 or 3, I'm going to post this, okay, in the community right now in the next 2-3 minutes, okay, is trace this code, okay. So you have the driver program, there's some how you calculate the cost, right? You need some procedure for that. And then that shows the code, right? So we have done enough tracing in this class, right? So I want you to trace this one. Okay. Now that is one aspect. Don't do it right away because I want to introduce you to the next one too before you start doing it. After you do that algorithm, then you have a dynamic programming solution for that. The first one is some algorithm that falls under the category called make it work. Okay, a lot of times that's what programmers do in the industry. They have stringent deadlines to meet. They're not looking for optimal algorithm. They just make it work. As long as it works, it compiles and it executes, the manager is happy and you can go home. Okay. And the QA and testing folks somewhere sitting in Ireland or India or even in US somewhere, they test it and then by the time they come back next morning, they'll find some bugs or performance bugs. When I say performance bugs, what I mean is they'll say it is not meeting the performance criteria and things like that. Then you go back and you try to refine the code. Okay. So this first step, think of it as make it work type of a thing. But we have a dynamic programming solution for that. So here is another piece of code for the same problem. Okay. With the same driver program and the same program for sum. So 2 variations of building the BST. Okay. One variation gives you some answer. The second variation gives you another answer. Ultimately, what are you printing? Cost of optimal BSC. So I want you to take those 2 algorithms, work in groups of 2 or 3, tell what the answer is when you do the first way and when you do the second way. Okay? Does everyone understand the question? Okay. Jntuk Kakinada asks, can you please explain the cost calculation again? Yeah, it gets to be very theoretical, and that's why I skipped it, but I'll try to do it, okay? Because generally when those formulas come, I don't pay attention to them because the formula should be given. Okay, but I can explain to you because I put the explanation here, right? So layman's explanation, how do you arrive at this, right? What we do is we take all the nodes, that is the algorithm. We take one, if there are 3, you take each one of them, make the root. Okay? See that R is root, okay, varies from I to J. Okay? So whenever we are making that rth node as root, we recursively calculate optimal cost from I to R minus 1. Okay, and then R is the root, right? Then you go to R plus 1 to J. So you see these 2 terms here, cost of I to R minus 1. Okay, and then cost of R plus 1 to J, because the range is from I to J and R is between I and J, right? That's why you see R of I. And then whatever you make the root, that root is nothing but the frequency K belongs to the root. When that K is equal to R, that is frequency of R. R is for root, right? So root is level 1, right? Remember what we said? Level times the frequency, right? That's what we do. So whenever you make something root, it's just frequency plus, since it's an ordered sequence of numbers, right? So you take 1 to r minus 1th element, compute the cost of that. Remember, it goes back to the substructure and subproblem, overlapping subproblems. That's what it is. Okay. Yes, so that is how you get this. So K, the first one is the root, and then you take all the elements optimum cost of rest of the elements up to that rth element, and then optimum cost of r plus 1 to j elements. Okay, that is the explanation for that code. Okay, now this code that you see here, what I will do is in the next, take a 2 to 3 minute break, stretch break, okay, and then I'll post it in the community. I can actually do it right now. I didn't check the size of the file. I hope it works. Let me share the screen. Let's put the driver program there. Right? Basically, you're calling that function there. The keys are 10, 12, 10, 12, and 20. And the frequencies are 34, 8, and 50. Okay. You may want to quickly write down this small function here, integer sum. For a driver program, there's nothing to write there, right? You're just calling that function. Just write down the simple statement, right? Sum, integer frequency, integer I, integer j. For I, integer I equal to j, k plus plus. There's those 3 lines, you write it down on a piece of paper. Okay? And write down the keys 10, 12, and 20. Just underneath them, write down the frequency 34, 8, and 50. Okay? It should take you no more than 1 minute to write those 2 things, what I just told you. In 1 minute, I'll switch the slide. Now, in case you don't finish the tracing today, you continue that. Before you come to the next class, I want you to finish tracing both this first algorithm as well as the DP algorithm, which I posted in the community now. And post your answers in the community, okay? Things here, right? I can actually I'll go mute. Let me put it here. I'll put that in for everyone, so that way they understand it. Okay. System variable, and the system variable, whatever int max that they have defined, right? So you're basically, it's a system defined variable, right? Like how your max integers and things like that. So whatever is the, where is the piece of code? Let me check. So you can assume some value for that, okay? That should really not come in the way of your testing though. Okay. I'd like to address Jntuk Kakinada's question here, right? You can write 5 types of BST. That's what I'm showing here, 5 types, right? So how do you calculate the cost? Okay. It's given right here in the slide, right? So what are we saying? We take the level where the node is and the frequency. So let's take the first tree here, 10, 12, and 20. Okay, what is the frequency? 10 is at level 1. We are assuming root is level 1. Okay, what is the frequency of 10? Frequency of 10 is 34. So 1 times 34. Okay, write it down here. I'll write it down here. Okay, I'm taking the first tree. See, 1 times, where is the star here? Star 34. Okay, I'm right. Plus 12 is where at the second level. So that is second level. Okay, this first is level. Okay, I'm just putting level there, right? And then whatever that first node there is at root, the frequency of that, I'll say frequency of 10. Okay, 2 times second level node is 12. So frequency of 12 is 8. 2 times 8 plus frequency of 20. So that is third level times 50. Okay. So it is level times whatever that node is at that level times the frequency of that node. Okay. Now, int max. So whatever that max has been defined is what I said. Let me check in the code where it is coming. Jntuk, if you still have questions. So if you apply the same logic here, you can see the cost of the fifth BSP, right? Because in the fifth BSP here, 20 is at the root level, that's level 1. So that's why level 1 times 50, frequency of 20. Level 2 has 10, frequency of 10 is 34, so level 2 times 34. Plus level 3, 12 is at level 3. Okay, so 3 times frequency of 12, 8, 142. Okay. Okay, now I go back to the code because somebody asked a question on code. ఎక్కడ చూసారు మరి ఇంటి మ్యాక్స్ అది ఓకే ఇక్కడ సమ్ మినిమం వాల్యూ అండి using that initialize minimum value. So you defined in the main program, probably you defined somewhere here, you defined int max, right? Okay, I know that what happened was I was sloppy. I did not copy what the int max value was, but I can, while you're doing it, I will compare, I will see my notes, okay? You downloaded the file. So you can see here, int max is whatever is the max int of the architecture, right? That's what it is. Okay. And then once you find the cost of the BST, okay, cost is less than min, then min equal to cost. So min is getting the very first time you're doing it, you're getting min equal to cost. Because when you're taking the maximum value, the hope is the cost that you're calculating may not exceed that maximum value. So that's the material for you. You should still be able to proceed just fine. Unless he's setting it somewhere else here. I'm just checking a few things here. Yeah, should be okay there. How are the students doing? Are they able to trace the code? Faculty members put something in the chat for me, so that way I know that they are able to do it or they are not able to do it. Sri Prakash, you are able to proceed with the explanation that I gave you for min equal to int max, or do you still have questions on that? Yeah, you can assume 999. Yeah, that should be fine. In this case, it should be fine. Actually, that's interesting. Why, if minimum cost can exceed the maximum value of the architecture, if it's depending on it's 2 raised 32-bit architecture or 64-bit, right? If it's a double, it's 4-byte for integer, 2 raised to 32, right? That is 4 gig or something? And the cost is going to go beyond that. It's going to give you, does it give you a segmentation fault? If you exceed the maximum number of supported by operating system, I think it will result in segmentation fault, I think. It won't even let you do, any faculty member who is teaching operating systems right now, they can answer the question. What happens if I compute a sum which goes beyond what is supported by the architecture? Give you some error or segmentation. It's a runtime core dump. If I'm not mistaken, because I used to teach instruction set architecture a long time ago. At that level of detail, I think it should give you a core dump, also called segmentation fault. Hope you guys are liking this exercise. It's fun. Guys, as Sri Prakash assumed int max is 999, let's all assume the same thing, okay? Of course, if you are a diligent student, what you would assume is int max equal to 0 also, and see what happens. There you go. See, Prakash, I was right. I used to teach HP precision risk architecture, and HP used to have its own operating system. We also had UX, HP UX. Of course, UX was before Linux, right? I actually taught Linux too, how to set up, configure, and administer a Linux system. So you're right, segmentation fault, there you go. I'm glad I still remember a little bit of my OS knowledge. And then we will move on, and that will still give us plenty of time to do the next 2 chapters, okay?